Hi students, welcome to another video on square wave generation. So in this video we will continue with the generation of square wave for different frequency and duty cycle. In the last case we have considered this as a circuit diagram with resistors R1 R2 as both 1.5 kilo ohm, which is providing the required value of V plus, and we used a timing capacitor of 0.1 microfarad, and we have used a fixed resistor of 10 kilo ohm, and we could able to find out what is the on time and off time, and we could also find what is the capacitor charging discharging and the output plus V sat and minus V sat. All the stuff we have just found out. Now let us continue with the same thing. So now this is the expression for the capacitor voltage, which we have discussed in detail in the previous videos, which is given by V final minus V final minus V initial e power minus T by RC. For T is equal to T on, the equation changes as per the initial and final voltages, and of course what is the voltage at T is equal to T on. So as per that, we have this as the expression for T on, where you're replacing this T by T on, and this R and C are replaced by the timing resistor and capacitors, and this is the expression for T off. What we'll do now is, so we try to I want you people to fill these tables. I'll be conducting the experiment using analog discovery. So I'll be using a DRB for this implementation. So what I'll do is I'll use a DRB here. So keep on changing the value of RT to 100K, 68K, 33K, and 22K, and 220 kilo ohms. So I will demonstrate, I will show the scope of the analog discovery, so that you can note down what is VTH, VTL, T on, T off, and the duty cycle as well as the frequency. These are the parameters that you can take from the scope of analog discovery, and use these two equations to find what is T on, T off, and then you can find what is duty cycle and the frequency. Then you have to compare these measured values with the theoretical values. So let us continue with the demonstration. So let me start with RT of 100 kilo ohm. So let me change this to 100 kilo ohm. Now I just change it to 100 kilo ohm. Since RT has increased to 100 kilo ohm, the frequency has reduced to a great extent. So let me change this to 10 millisecond. Now what I'll do, I'll just make a single run. Okay, now what I'll do, okay, I'll take a screenshot of this and then also store it in one of my doc file. So what I'll do is, let me go here and then create a new doc file where I can be okay. This is 1 second. So sorry for that. Okay, now I can edit. This is trigger. The first reading, I'll just paste it here. This is my, okay, let me just take this screenshot. I have taken a screenshot corresponding to 100K. Now I will say RT is equal to 100 kilo ohm. So let me just copy this and paste. Okay, let me just go here and then do it for first RT value, which is 100K. Sorry, let me just take the screenshot of this. I have taken the screenshot. So now let me go back to this, and then this is for 100K. So you can know what are the values that are corresponding to, we know what are these. So this is VTH, this is VTL, and this is my plus VSAT, minus VSAT, frequency of the signal, duty cycle, the positive width and negative width, that is T on and T off, T on and T off. So these are all the timings for 100 kilo ohm as my RT. Next reading that I'm supposed to get is for a value of 68 kilo ohm. So let me adjust it to 68. 1 2 3 4 5 6 7. This is 68. 6 1 2 3 4 5 6 7 8. Fine. So now I'm having a resistance value of 68 kilo ohm. So let me again run it. This is the previous one. You can see now the timings have altered. So what I'll do now, so I'll take another screenshot. This is corresponding to a value of RT which is 68 kilo ohm. This is corresponding to 68 kilo ohm. So I'm just pasting it here. So you know the corresponding values of VTH, VTL and all those things. Let me again come back here. So let me set it for the third value what I'm supposed to keep, which happens to be 33 kilo ohm. So I'll make it this is now, sorry, so it is now 30. Okay, this is 0 1 2 3 30, and this is 1 2 3. So this is 33 kilo ohm. Let me go back to my wavegen. Let me run this now. Okay, now this is, maybe we can just slightly change this to so that you can clearly see this. Okay, now this is, I will again run just for clarity. Note all these parameters. Of course, this is for a value of RT is equal to 33 kilo ohm. So let me take the screenshot of this, and then this corresponds to value of RT, which is 33 kilo ohm. Let me just paste it here. This is for 33 kilo ohm. Use these values for calculating the theoretical values which is intended to be found here. This is, you're supposed to find all these values for which you should know what is VSAT minus VSAT, all those stuff. So next it is 22K. I'll make this 20. This is 2. Now I made it 22K. So let me take another screenshot corresponding to this. Before I take the screenshot, let me run this one. Okay, now this is ran. These are my changed values. Let me take another screenshot and then put it as for 22K. So this is now 22K. Next, this is my readings. Next is for a value of RT is equal to, let me see what is the value I'm looking for. So this is 220 kilo ohm. So I'm intentionally making it large resistance so that of course you can do it for any value. Of course, in the previous video we have seen the limitation. You cannot go for very low values. The frequency limitation is there, so I cannot go for 5 kilohertz or so on. So now I made it 220. Let me make this 220. Now this is 100, 200. This is there. Okay, fine. Now this is 220. Let me go back to this and then run. So since time period has increased, so this will change. I will make it 10 millisecond. Let me again run. Okay, this is my okay, I'll take another screenshot. This is corresponding to 220 kilo. Okay, I'm done with now. Since you have these many readings corresponding to different values of RT, next now you can look at the video, and for each and every value of RT you can pause it, note the values of these VTH, VTL, T on, T off, duty cycle, frequency. This you get it from ADKit, and use these two equations to find T on, T off, and ultimately calculate duty cycle and frequency. So you can see one interesting observation is the duty cycle of all the readings will be around 40%. So that you can notice, because we are not changing the duty cycle. Duty cycle remains same. So that's what is one of the interesting things that you are supposed to notice. Now let us move on to another category of this square wave generation, where you're supposed to generate signals of different duty cycles. So I'm looking at different duty cycle. When I say duty cycle, so this is what I'm meant. I think okay, now by this time all of you know what is the meaning of duty cycle and all those stuff. So we know that for a square wave, if this is square wave having this as my time axis, suppose if this is my on time, now this is my off time. You can see I'm making my off time very small compared to the on time. So this is T on, so this happens to be T off. So duty cycle is very less. Sorry, so duty cycle is very large because T on is more, because we know that duty cycle is nothing but T on by total T. When T on is more compared to the T off time, my duty cycle will be greater than 50%. Now I can have a situation where I can have this as small whereas this is more. So my off time is more and on time is less. You can see this is T on, this is T off. So this is 0 voltage, this is 0 voltage, this is plus VSAT, this is minus VSAT. My T on is less compared to T off. Now duty cycle is less than 50%. This I can get it provided if I have different charging and discharging paths for the capacitor to charge and discharge. Now in the previous circuit, we know that we had only one path for this capacitor was going to plus V side through this RT, and it was discharging to minus V side through RT only. The charging discharging path were same, meaning charging rate and discharging rate were same. So that's why we had a constant duty cycle of 40% throughout different values of RT. Now that's what, okay. Whenever, of course, in the last we have done, maybe you can just have a look at the screenshots and then try to identify their. Let me just zoom this. See here, the duty cycle is almost 40% for a value of RT so and so, RT 220K. See, now this is for 22K. Just have a look at the pulse width. Sorry, positive duty. It is again 40%. This is for 22K. I can see this is for 33K. Just again have a look at this positive duty. Again 40%. Next you can see this is for 68K. It's again 40% close to. And this is 100K. This is close to 40%. The duty cycle is the only parameter which is remaining constant for all these things. And of course, I am talking about the timing one. So duty cycle remains a constant because the charging and discharging paths are not changing for a particular value of RT. So what we are trying to do, what we are trying to achieve is, how do we get a pulse, a duty cycle which is greater than 50% and less than 50%, something like this situation. In order to do this, I should have different paths for this capacitor for charging and discharging. You can see now I'm using two diodes in a different direction. When the output is plus VSAT, this will conduct. So that's what. So when the capacitor is charging, we know that that corresponds to on time. So that's why this resistor, I'm naming it as RT on. That is, this D1 will be on during the positive VSAT, and D2 will be on whenever the output voltage is minus VSAT. So that's why this will be on, meaning discharging will happen through RT off. So in this expression, whenever I am having T on, I need to consider a resistor which is responsible for charging the capacitor, which is RT on. So while finding off time, I have to consider that resistor which is responsible during the discharge time. So we are assuming that the resistance of the diode when it is on is negligible. So that's why I'm not including that RT off plus diode resistance, because that diode resistance will be very small during on condition. So this will be used during charging the capacitor. This path will be used during discharge resistance, discharge path. Now, if the values of this T off and T on are different, then duty cycles will also be different. For that, I'll make slight change in my circuit diagram. So let me have this circuit diagram and then try to do that. So let me just do the same thing now. So I'm now connecting this to. So this is connected. I will connect this here. So I'm using one of the resistor as fixed one, and I'll use the another one as a variable. So variable is now T off. Okay, Okay, let me make that as, okay, let me just, I'll make the off resistance as variable. The okay, sorry, the off resistance is fixed, which is 5.6k. The on resistance I'll vary. So I'm just doing the same connection here. So this is done. So this is now okay. So I'm connecting these. Give me a minute. I'm connecting them. So it's connected now. So I will change RT on using the DRB and try to find out. So now, okay, let me go back. Now I'm using this RT off as 5.6 kilo ohm fixed. Now this I will make it different resistances. So let me take it as first value as maybe 3.3 kilo ohm. Let me make it as 22 kilo ohm. Let me make it as maybe uh, maybe 100 kilo ohm. Let me take it as 1.5k. Let me just take these values. So what I'll do now, for first let me go to 3.3k as my resistance. Okay, now or okay, let us see. So let us see the limitation that I may end up with. This is 1, 2, 3. This is now 1, 2, 3. So this is, I kept this as 3.3k. This is already 5.6k. Let me just go here and try to find out. So let me run. Okay, now you can see it is totally different. Just have a look at the duty cycle. That's what is interesting now. Let me further make it maybe 500 microsecond. It is interesting to see now. So let me run. See now the duty cycle has reduced to 27%. The duty cycle has now gone away from that 40%. Now it has become 27%. So now again, this is for a RT on of 3.3 kilo ohms. So this is for a 3.3 kilo ohm resistance. So what I'll do, I will go here and then this is for a different duty cycle. So this is RT on. RT on is now, because RTF is fixed, RT on is now 3.3k. This is now 3.3 kilo ohm. Sorry, 3.3k. Let me just take the screenshot of this print screen and go back here and then paste it here. And let me take again. Let me just copy this for. Okay, now this is okay. This is for what the value now? Let me take it as 22 kilo ohm. So that's what I'm just listed there. It is 22k. I will go back to this and I'll make the resistance as 22k. Where is 22? I'll make this. This is 1, 2. This is now 1, 2. Fine. So this is 22k. I will run it again. You can see now it is a totally different duty cycle. Now maybe you can just make this time period 1 millisecond so that you can comfortably see them. So you can see now the duty cycle is 67%. It is no more 40%. Now we are intentionally changing the duty cycle more than 50%, less than 50%, all those stuff. So let me take this as one of my screenshot. This is for a RT on of 22k. I'm specifically saying that this is RT on. RT off is fixed as 5.6 kilo ohm as per this. You can see RT off I'm not changing. I'm just keeping this as 5.6. So this is 5.6 kilo ohm. This I'm just keep changing as per my readings. So my second reading is over. So let me take the third reading, which is 100k. I'll make this. This is now 100. Okay, now it is 100k is my RT on. Let me go back to this and then take single run. Now since it is not covering all the cycle, now let me make this 5 and then again run. You can see now the duty cycle is almost 90%. Positive duty cycle is 90%. You take a screenshot for this. This is for the value of RT on. This is for RT on of 100 kilo ohm. So this is now that value. So let me do it for another value of this, so which is now 1.5k. So this is my second, third, fourth value. So for a RT on of 1.5 kilo ohm, let me find out how much is this. So it is 1.5k. This is now 1, 2, 3, 4, 5. Let me make that 100k as 0. So now it is 1.5k. Let me go back to this and then run here. You can see it is too much. So what I'll do, I will change this scale to a lower number. So now let me make it more clearly. This is fine. Okay, let me again run. So you can see the duty cycle is hardly 16%. So where is 90%, where is 16%? Because my RT on is very small. So this is the positive duty cycle. I will take a print screen of this and I'll just go back to this. This is for a RT on off. This is for a RT on off. This is for a RT on off. How much? 1.5k. So this I'll paste it now. So now you can see these are my values of different readings. So now again, so as I mentioned, from the scope you get all these values tabulated. Use this equation, use the corresponding value of RT on and RT off. Try to know what is this duty cycles T on, T off and frequency. So that will give you a good hold on how to conduct the experiment of this square wave generation for any duty cycle for that matter. So here we are considering, okay, you need to measure what is plus Vsat, minus Vsat, VTL, VTH, whether this is a common measurement, whereas these things will be keep changing. You can just have a look at, okay, whether these are also keep changing or they are the same or not. Thank you.